Hello, welcome to the next lecture. Last time I gave you an introduction to the course and I provided a bird's eye view which was an overview of the hardware, software and sensation and perception parts of virtual reality. So during the software part, one of the key things that I mentioned was the alternate world generator. So today I want to go into the basic mathematics, the kinds of modeling and transformations that we need to do to set up an alternate world generator. So today's lectures will be more fundamentally oriented, I will say. With geometric modeling of alternate worlds. So the alternate world generator in some sense has to simulate or reconstruct some kind of world, right. So it may be simulating a virtual world that has geometry, it has physics, and the geometry and physics has to look reasonable to your brain, right. It has to appear reasonable to your brain or to your perception when you use virtual reality, when you're in this kind of experience. So we may be simulating a virtual environment, or you may be capturing a real physical environment in some way. It could be far away, or it could be recorded, or both, and you're transmitting that through this kind of head mounted display, and that provides another example of virtual reality. So what we have, I'll say let W be a 3D world, right. So I mean that W is some subset of R3, so I'll just start doing mathematics in Cartesian coordinates on the reals in 3 dimensions. Let me define a coordinate system. So we'll have x going horizontally, we'll have a y-axis going upward, and we have z coming out of the board, done in a way so that we have a right-handed coordinate system. So I'll prefer and use right-handed coordinate systems all the way through. In graphics and rendering, it's sometimes preferable to use left-handed coordinate systems, and in DirectX, if you're doing programming in that, it's left-handed. If you're doing programming in OpenGL, a lot of other systems, it's right-handed. But most of math and physics is right-handed oriented, so I want to stay in that way. Also, I'll follow the conventions used in the game industry and throughout much of graphics, which is that the y-axis is up. Throughout most of engineering, I think the z-axis is up, but we're going to stay consistent with that so that whatever you apply from game engines and related things, it ends up being consistent. So this is a 3-dimensional world, and so each point in this world has coordinates x, y, z element of W. So I would just have, I'll be describing points with x, y, z coordinates. So the world has 2 kinds of models. All right, the first main distinction I want to make here is, one, we have stationary models. So this means, as the name implies, they never move. So this can correspond to buildings, walls, trees, assuming the trees aren't swaying in the wind, right. So think about things that when you put them into the world, they remain fixed all of the time, right. That's the simplest case. In this case, they're described in the world coordinate frame. And so we can just make up these x, y, z coordinates for whatever points we want to describe for these stationary models and leave them alone the whole time. One thing I should say, if you're building a virtual world, I highly recommend scaling these axes in a way that corresponds perfectly to the world that you're making. So I highly recommend, for example, if you use the metric system, then measure out everything in meters or centimeters, whatever it is that you'd like to use, so that you can always remember what the scale correspondence is between your virtual world and the real world. Unless you're doing interesting VR experiments where you want to change your scale entirely, which is interesting by itself, I would rather do that as another transformation that you apply to this. But it's very nice and helpful to keep the numbering in here, let's say, consistent with measurements in the real world. So that if you draw a chair, for example, the chair ends up being the right size if you're trying to capture a chair from the physical world and bring it into the virtual world. You don't have to study it, look at it, you end up with problems of perception of scale, and it gets very difficult. So it's nice to keep these coordinates like that, match them as they would be in the real world. All right. So 2, the other kind of model inside of the world are movable models. And in this case, these models have a space of possible transformations. Right, space of possible transformations. You write that down here. So this may correspond to many moving things. It could be the avatars, representations of yourself, anything else moving around, other characters, animals, moving bullets, blowing leaves, all sorts of things. And usually these are composed of rigid bodies. So imagine having a bunch of rigid bodies attached together. So usually composed of rigid bodies each of which is defined in its own body frame. Right. So we will not directly use the world coordinate frame, but each body will have its own frame, and then we will imagine a movable model as being a collection of one or more rigid bodies. So they could be attached together just like a human skeleton, let's say, where we have each rigid body may correspond to a particular link, and the links are all joined together by joints, and we end up with some kind of movable structure. It could just be a single rigid body that simply moves around through the space. Maybe you have a chair that can be moved around, so it's rigid by itself, but it's a movable body. The character may be able to come up, grab the chair, and move it somewhere. So in these cases, we have to talk about a space of possible transformations that can be applied. In order to do that, we start off by describing it in the body frame. So we generally have 2 modeling choices. When we're making geometric models of these bodies that are in the world, whether they're stationary or movable, whether they're stationary or movable, one choice is to have what's called a solid representation. And the second one is what's called a boundary representation. So in the case of solid representation, we have 3-dimensional primitives. Right, so the most basic description unit we have represents some 3-dimensional chunk of the world or of the body. And in the boundary representation case, we have 2D primitives. There are lots of details to this, lots of interesting technical complications, and a lot of trouble comes about based on which representation you choose. You solve some problems and then other problems emerge. And I'll give you a little bit of a hint of that today, but I will not be covering it in full detail. So one thing to think about with regard to this is think about obstacles. And collision detection. Right? In the real world, when I walk up to this table, my motion is physically obstructed, right? So that's one kind of obstacle. If I put this notebook in front of me, I also have some visual obstruction as well, right? And you could have two, these could be independent, right? I could have some fog that does not obstruct my motion, but it just obstructs my visibility, right? I could have, what's an example of an obstacle that obstructs my motion but not visibility? Glass, very good. So I can look through glass and I get obstructed, maybe surprised by that. So those are two different kinds of obstructions. You could model these things and represent them. I haven't talked about rendering or graphics yet. We'll have to get to that part when we talk about drawing the world in a way and presenting it, drawing it in a way that's appropriate for your vision sense. We haven't gotten to that yet. We're just describing the geometry of the world. So with regard to these two choices, having one body, let's say, represented like this, and I have another body that's here. In this case, I would say they are in collision. Right? Because they intersect, right? There's a non-empty intersection. Now, if I have some kind of solid representation, and I'm only drawing this in 2 dimensions, hence the solid representation looks 2D and a boundary representation should look 1D, right? So if I just think about representing these by their boundaries, just the outer perimeter of the yellow blob and the white blob, then these also intersect at these points here, right? So if I were going to do some kind of intersection test, I could look only at the boundary. Maybe I break this into tiny line segments and I do line segment tests, or maybe I get a little more clever with the algebra. I realize these are circles, so I could do some circle intersection tests. But what happens when I have this case? Right? So in this case, if I'm using a solid representation, I may be able to tell very quickly, depending on how I've decided to represent it, that the yellow disk is in fact in the interior of the white disk. But if I have a boundary representation, there's no intersection of the boundaries. Right? So it's just something very important to think about. There's some kind of meaning behind these representations, and it's somewhat implicit. And then later, as you start developing, you realize some of the shortcomings and problems. Let me give you an example that gets a little bit worse. It may be that I have a boundary representation and it has mistakes in it a little bit. So this is the boundary representation that I have of one object or body, and well, maybe the other one is fine and looks like that. So that's the boundary representation of that one. And I'm still trying to infer whether or not this yellow disk is inside or outside of the white disk. And it may be that I have a perfectly defined disk here, but out here, because I have these breaks, I'm not even sure if there is a well-defined notion of inside or outside, right? What does it mean to be inside or outside of this? How can you define that? If this is a closed curve, then by the Jordan curve theorem, there's an inside and an outside, and that's all there is. It very nicely partitions the space into 2 regions. But when there's this break in here, it's not very well defined. And you can imagine that the same thing happens in 3 dimensions, and it's much worse. And you have to think about, where does your model come from? If you're drawing the model yourself, maybe using a design tool, maybe using Maya or Blender, and you're making your own models, perhaps you can get everything very consistent. This is called model coherency, where this particular example I've given has a lack of coherency. You meant this to be a closed curve, but it ends up getting broken. So you have to ask yourself, what's the coherency or perhaps consistency of the model? If you're extracting this model using depth cameras, right? Maybe you have computer vision algorithms running, you're also getting depth information, you're trying to build some kind of surface description. What do you think the chances are that there's going to be little holes in your data? Right? And that's going to make a mess. So you may have to do a lot of work to build a coherent model. You may have to do even more work perhaps to build a nice solid representation of it. But then when you do that, then it'll be easier to determine collisions. So these are just some of the kind of difficulties you end up with. Also, because it's difficult to know what side you're on of these boundary pieces, it gets sometimes difficult to render surfaces in computer graphics, because you're not sure whether the surface normal that you're looking at is pointing outside or inside of the object to be rendered. There's a lot of difficulties with that if you do some rendering on your own. It often mistakes come up because the surface normals are pointing in the wrong direction. So these are some different choices. At the highest level, I'm going to only work with boundary representations, even though I think solid representations are cleaner in a lot of ways. One of the reasons why we should talk about boundary representations here is because that's what's done in primarily in game engines all the way down to GPUs. So the graphical processing units that are in our computers are geared for boundary representations, and in particular representations that are made of 3D triangles. So why don't we pick the simplest case, boundary representations, and the two-dimensional primitives are going to be triangles that sit in three-dimensional space. So I call them 2D because it's a two-dimensional triangle. It's not a three-dimensional simplex or pyramid of some kind that's sitting in space. It's a two-dimensional surface that sits in three-dimensional space. So it's a 2D primitive. So let's use a triangle primitives. So in order to describe a triangle, we may mean, well, we generally mean this two-dimensional surface. It's assumed to be linear. It's just part of a plane. And so all you need to define are the vertices of the triangle, x1, y1, z1, x2, y2, z2, x3, y3, z3. Right? So I can start defining triangles like this. If I put them into the world, I define them in the world coordinate frame for stationary models. And again, if they are movable models, then we define them in the body frame, and then I'm going to say what to do later on how to transform those. There's also some common tricks for gluing triangles together in order to save space and to make more efficient data structures to access all of the triangles in a quick manner. And one thing that may happen is the triangles may be glued together to form strips. So you could have a strip of triangles and do operations on that. More generally, you may find the triangles are put together in some kind of mesh. And there are all sorts of interesting issues in terms of what kind of properties should we maintain in that mesh in order to make the computations that we perform later if we're studying or let's say solving problems of rendering to determine what the lighting should be across the surface. We'd like to have not too many triangles. We'd also like to represent the surface very well. If it has a lot of curvature, we might need to make the triangle smaller. We'd also like to avoid having very, very thin triangles. If we captured a surface from a depth camera, how do we build a nice representation of this? And there are a lot of algorithms from the field of computational geometry. You can study these. People are very interested in starting from raw data and then building nice surface representations like this, boundary representations, especially not having incorrect holes in the data. So when you put these together, when you make strips or a mesh, if the model is coherent, then many of the vertices are shared. So that reduces the overall amount of data storage, and there are very clearly defined adjacencies here between triangles. And so you can make data structures with pointers that move around. One example is a doubly connected edge list, which computational geometers have developed, where you can very quickly move across and propagate computations across these surfaces that you might need to do. So, so that's about all I'll say about basic modeling and primitives. Are there any questions about that?